Hey, this is Professor Lemire. This is the promised Reynolds Transport Theorem derivation. Apologize for the late go of this, but here we go. The presentation that I've prepared for you here follows very closely that's given in the book, so I'm going to give it to you right now as a reading assignment for afterwards. I'm going to ask you to read section 4.4 in the Munson book, and hopefully you'll find that what I'm presenting to you here follows closely what he's got out there, and hopefully reinforces some of the concepts that are going on there. Okay, Reynolds Transport Theorem. First, I'm going to start to try and make a case for why we need to have a theorem that does what this one does. I'm going to define it. Then I'm going to go ahead and prove it in three different forms. All three forms we're going to be using in this course, so it's important that you master each one of them. Okay, so the Reynolds Transport Theorem. Okay, and this is the only part of this presentation where I'm actually going to spell it out all like this. The rest of the time I'm going to call it RTT. So the RTT, what is it? Well, it's a mathematical tool. Mathematical tool that we use to go between the Lagrangian representation of the fluid and what's the other one called again? Eulerian, you got it. That's close enough. Or vice versa. Okay, so the question that comes to mind then is, well, do we really need that? Is this what's the problem between going back and forth between those two representations? I didn't know there was a problem. Well, yeah, there can be a problem. So before I give you a statement of the theorem, let's look at what it actually does. So, oops. Don't want to do that. Come on, get out of there. Okay. Let's look at a fluid system that has mass m. Okay, in a proper grid system here. There we go. That'll look good. So I've got a fluid system that looks like that. You should feel pretty comfortable as to what a system is. Versus what a control volume is. So this is a system, which means that we're tracking a fixed number of particles within this blue envelope right there. That system has a volume that I'm going to call V. It has a surface that circles this volume that I'm going to call S, so surface. Both the surface and the volume, of course, can change as a function of time because we're tracking a fixed number of particles. We're not tracking a fixed volume. And on this surface, let's say I pick a small little element, ds of that surface. If I express the normal to that little element, it would look something like that. So this is a vector, unit vector, normal to the surface ds that I've just defined. And the fluid may have a velocity that's not aligned with that normal. That velocity could look something like that. Okay? All right. So this is the system in question. I'm letting v be the velocity at any point on the surface of this system. N is a unit normal as I just defined it. Let's let b, all right, the letter b represent any extensive, it's important, property of the fluid that's in this element right there. Well, this didn't work here. Okay, that's in this in our control volume. Let's let the mass of the control of the system be m. Okay, and let's let little b be the intensive counterpart to B. Okay, so that means that little b is equal to big B divided by m. All right, so far so good. So the total content of B in the system is therefore the integral over the volume that we've got of little b times dm, right? But dm is nothing more than rho times dv. So I've got the integral over the volume of b times rho dv, same thing. And we're normally going to write this as the integral of rho times b dv, just for convenience sake as we move forward. Okay. So the question that we pose ourselves and that we're going to need Reynolds Transport Theorem for is, how exactly does this B property, this extensive property of the system, change as a function of time? So B, of course, can be a function of time. It doesn't have to stay constant as a function of time. So it's a function of time. Of course, it could also be constant with time, but in general, it can be a variable. So let's look at that question first and have an example that shows that we might have a problem here for which we need this so-called transport theorem. For a system, the value of B of the system is equal to this integral that we have up there, which is the volume of the system times rho times B times dV. So therefore the rate of change of B with respect to time must necessarily be the derivative of that integral. All right, so taking the derivative of that integral actually turns out to be a little trickier than what might seem at first. So let's define a control volume that matches the system instantaneously at some time t. Okay, so for a control volume that matches the system, I'm going to have B of the control volume is equal to the same thing, just a different volume now. And the rate of change of that property over the control volume is going to be just like it was for the system, except again the integral is taken over the control volume specifically, not over the system anymore. And what we want to notice critically is that these two rates of change are not necessarily the same. And that's what we want to highlight here. d dt of the extensive property over the system is not equal to d dt of the extensive property over the control volume. So the best way to show this is to look at an example. If we can find one example for which the statement here is true, then that means that we can never assume that the rate of change of the system is the same as the rate of change of the control volume. So this is an example that's in your book. Also, it's as good as any as to illustrate this this concept. So here we go. Example 4.7, and what we're looking at here is a fire extinguisher. All right. So the system in this fire extinguisher is the stuff inside the fire extinguisher at some time equals 0, and I'm going to define a control volume that sort of circles this whole system. All right, so the system and the control volume, the system boundary and the control volume all match at time equals 0. Then at some other time greater than 0, I squirt some of the fire extinguisher stuff out of the fire extinguisher. Here it is. So now what's the system? Remember, we're tracking fixed number of particles. So the particles are what's left in the fire extinguisher plus whatever is in that cloud that went outside of the fire extinguisher. Okay. Control volume, however, didn't change. So let's look at what happened at a specific case of dB cis dt and dB CV dt. Okay. Notice, by the way, I'm using, I don't know if I made that clear anymore. When I say, I'm not saying control volume anymore, I'm saying CV. Okay. So we can pick any property, extensive property that we want for B. So let's pick the mass of the system. That's an extensive property, right? That means we can add it continuously over an entire volume, and certainly we can add the mass over an entire volume and get the total mass of a system. So let B equal the mass of the system. Okay, so that's equal to big M. So therefore, what's little b? Well, little b is defined as big B over M, so that's going to be big M over M. That's going to mean that B is 1, little b is 1. Okay, easiest case to take. Let's see if we can get a contradiction with that. So for the system then, remember we're interested in the rate of change of B with respect to time. D dt of B cis is equal to D dt of the mass of the system. Oh, that's starting to sound good here. Sounds like a law that we've talked about before. Is equal to d dt of the integral over the volume of the system of rho dV. Okay, again, rho dV here, that matches how we defined dB cis dt up here with B equal to 1. So everything's consistent, makes sense. The integral of rho dV is in fact the mass. Okay, and remember the system mass is fixed. All right, now for the control volume, I'm going to use a different color here for the control volume. For the control volume, we're looking at d dt of B over the CV, which is equal to d dt of the integral over the CV of rho dV. And remember, the control volume here is the tank. Control volume is just what's inside the tank. So since no mass leaves the system, this first integral must necessarily be 0. Right? We're tracking a fixed system, so therefore that one is 0. However, for the control volume, some mass did leave the control volume, and so therefore that integral, the amount of mass that's in the control volume, must necessarily have gone down, so it must be less than 0. It must be less than 0 since some mass left the control volume. And so we've proven with one example that the rate of change of some property, extensive property of the system, is not equal to the rate of change of the same property applied to an arbitrary control volume that matched with the system at some previous time. And that problem right there is the reason why Reynolds Transport Theorem was developed. Okay, what does it do then? It relates those two representations. It finds a way to make them equal. Finds a way to make them equal. All right, so that takes us right into the derivation of the Reynolds Transport Theorem. Okay. All right, in order to do that, I'm going to pick another nice little diagram here. And let's go and put that up there. Okay. All right, another illustration is going to help us to come up with this mapping, if you will, between the Lagrangian or system approach and Eulerian and control volume approach. So what we're looking at here is called a diffuser. What's a diffuser? It's a piece of ducting that reduces the speed of the flow. Okay, so as the flow moves from left to right, its speeds generally decreases. You can convince yourself of that if it's not obvious to you, just by looking at Bernoulli's equation. You're not all experts on that on this system. So what we have here on the left-hand side is a picture of the diffuser with a dashed blue line representing our fixed control volume, and some stuff that comes into the control volume at a speed v1 on the left-hand side, and I'm calling that side the plane 1, so it has an area a1 as well, and all the properties at 1 are subscripted 1, so rho 1, a1, v1, etc. And on the right-hand side, they have the property underscored subscripted 2, so it's got an area of a2, speed v2, etc. All this is shown to you at some time equals t. All right. That time equal t is picked so that what's shown in green is a plug of fluid that matches the control volume exactly. Of course, that region of fluid, that system of fluid, is going to move if we go a moment later at a time greater than t. So the second picture here represents what's going on at some time equals t plus delta t, and as we see in this picture, the slug of fluid has moved away from the control volume, and there's now some distance between the left edge of the control volume and the left edge of the system, and the right edge of the control volume and the right edge of the system. So the system has moved away from the control volume, and we're going to look at 3 different regions in this new setup at t equals t plus delta t. One, region 1, and I'm looking here at the gap that's left between the control volume and the system that's moved away from it. Region number 2, which is the part of the system that's still within the confine of the control volume. And region number 3, the part of the system that left the control volume. Okay, so 1 really represents stuff that wasn't in the control volume initially and that came in to replace the system that left. All right. So at times equal t, both the CV and the system are the same. So let's write that down. At time equals t, then we have whatever extensive property of the system is equal to the extensive property of the control volume. However, at time, this is time equals t, at time equals t plus delta t, not so true. We have B of the system at t plus delta t. What's it equal to at that time? Well, it's equal to whatever is in region 2 of the flow shown in this picture and region 3 of the flow shown in this picture. So that's B of 2 at t plus delta t plus B at 3 of t plus delta t. Okay. We remember, however, that B at 2 is part of the control volume, not all of it, part of it, right? 2, we defined it to be that part that's confined between the edge of the control volume and wherever the system is still in it. So that's equal to B of the control volume minus, the only part that's missing is the part that's at 1. All right, so we can then express the property in the system at t plus delta t as B of the CV t plus delta t minus B1 t plus delta t plus B3 t plus delta t. All right, so this is B of the sys t plus delta t. I'm going to go ahead and call that equation 1. Great. All right, here's our equation 1. Okay? So if we want to look at the change in the system property over time, what we've got is dB sys over d time is equal to the change in B sys over delta t, taking the limit of that. Delta t approaches 0, which is equal to, since we now know what B sys at t plus delta t is, it's equal to this whole equation 1 minus B sys from before divided by delta t. So I'm just going to write B sys of t plus delta t minus B sys at t. Right? We're taking that ratio right there. We plug in from what we've got for equation 1, which is BCV of t plus delta t minus B1 t plus delta t plus B3 of t plus delta t minus B sys at t. All that divided by delta t. All right. Right off, I want to draw your attention to this last term right there, B sys at t. What do we know about B sys at t? That's the value of the extensive property in the system at time equals t. But at time equals c, the value of B in the system is exactly equal to the value of B in the control volume, because the system and the control volume are the same. So I can replace that last guy with BCV. Oops. At t. This is convenient because I got BCV at t plus delta t over there, and you see where, hopefully you get an idea of where this is going. I'm now going to break this sum down as BCV t plus delta t, bring this last term over, minus BCV at t, all that divided by delta t, minus B1 t plus delta t over delta t plus B3 t plus delta t. All right, that's what the rate of change of B sys is. Let's look at each of those terms separately, 1, 2, and 3. So term 1, in the limit as delta t approaches 0, is of course the derivative of B in the control volume, and that's really what the term that we were saying before is not equal by itself to the rate of change of B in the system as a function of time. So it's not equal, we see now, because there's two more terms that need to be considered as well. So term 2 now represents the rate of the flow of B, because we're looking at B at T plus delta T, out of the, into the control volume, into region 1 specifically in the control volume over the time delta T. So what is the volume that flew into region 1 during time delta T? We're going to call that volume delta V1. That's the volume that enters region 1. And what is that equal to? That's equal to whatever the area of 1 is times dL1. We defined what dL1 was. That's the volume that passed through area 1 during time delta T, and that's the volume that filled in during that time. Well, if it's the volume that came in through area 1 during time delta T, that must be equal to A1 times the velocity at 1 times delta T, right? And off we go. So therefore, the value of B T plus delta T is equal to rho 1 B1 A1 V1 delta T. And the limit, as delta T approaches 0, of B1 of T plus delta T, or delta T, is equal to rho 1 B1 A1 V1. Alright, this is taking way too long. But we're almost finished. We're going to push this to the end here and we're almost there. Term 3. Okay, so the last term, term number 3, which is this guy over here, represents the amount of B that left the control volume during that same amount of time. Stuff that left control volume during that same amount of time. So what we've got is B3 of T plus delta T is equal to rho 2 B2 delta V2, and that delta V2, just like before, is equal to A2 V2 times delta T. So the limit, as delta T approaches 0, of B3 T plus delta T over delta T is, like it was above, rho 2 B2 A2 V2. That's our term number 3. And voila, we've got the whole thing. When we put it all together, we've got the rate of change of B in the system over time is equal to the derivative of the integral over the control volume of rho B dV minus rho 1, that's our term 2, A1 B1 V1, plus rho 2 B2 A2 V2. And that, folks, is our first form of Reynolds Transport Theorem, what we also call the restricted form. And the assumptions for the restricted form of the Reynolds Transport Theorem are A, that there's only one outlet and one inlet control surfaces. B, that the properties are uniform. Across both the inlet and outlet. And C, that the velocities are normal to the inlet and the outlet. Alright, I'm going to quit there. And we'll talk about generalization of the theorem separately. Okay, I'll see you tomorrow. Good night.